And our goal today is to prove Vizing's theorem, right? So I just want to remind you of the question I had asked at the end of the last lecture. So let's see if any of you have an answer to this. So, right, so I'd asked you the following question. Supposing I have a proper k-edge coloring of the graph G minus V, where V is some vertex, then can you phrase in terms of bipartite matchings how, under what circumstances, you would be able to extend C to a proper k-edge coloring of the graph G? Does anybody have a guess? So can you formulate this? Can you formulate the answer to this question in terms of bipartite matchings? Did either of you get a chance to try this?
I
Okay.
didn't.
Yeah, go ahead.
Okay.
You did not? Okay.
Oh, yes, I did not.
Okay. How about you, Ravi? Any suggestions on how to do this? Okay, neither. All right. So let me tell you how you would do that in terms of bipartite matching. It's fairly straightforward, actually. Um, so let me make a different drawing here. Okay. Supposing this is my vertex V, and let's say V has a bunch of neighbors: V1, V2, V3, V4, V5. Okay. Great. Um, all right. So we have this graph as G minus V, right? And what we have is a C, um, proper K edge coloring of G minus V. Okay. All right. So what I will do is, I will create a bipartite graph as follows. H is going to be my bipartite graph. One color class will be the neighbors of my vertex V, and the other one will be my colors. So that will be 1 up to K. Right? I have a K edge coloring, and I want to get another proper K edge coloring of the whole graph with the vertex V. Right? Now, okay, so let us take a look at this graph. So in my bipartite graph, I've got V1, V2, V3, V4, V5. These are the neighbors of the vertex V. And on the right hand side, I have all my colors. Let's suppose I have 7 colors. Okay, so these are 1, 2, well, it is K colors, so let's just keep it K. Okay, and I will make two vertices on the left and the right adjacent if um, if those colors are available at that vertex, which means they are not used. So for example, in the coloring of G minus V, right? Supposing I have a red color that is used here, supposing I have a green color that is used here, and let's say I have blue that is used here. But let's say I have a fourth color, yellow, which is not used at V1. Okay, and orange, let's say. So what I will do is, you can think of red as being color 1, green as being color 2, blue as being color 3. Sorry, green is color 2, my bad. Supposing 2 is green, then you have blue, and let's say the fourth color is yellow, right? Or orange, it's more visible. Supposing this is number 4. And let's say at the vertex V1, the orange color has not been used. I'm just using, let's say, 3 colors, red, green, and blue. So in that case, I will make V14 an edge of my graph. Okay. Whenever a color is available, I will put those edges in my bipartite graph. Okay. So we construct a bipartite graph as follows. Um, we will put U adjacent to I. So U is in the neighborhood of the vertex V, and I is one of the colors. I is a color. In the bipartite graph H, if and only if color I is available at U as per the coloring C. Okay, and I claim the following: that um, a proper KH coloring of G minus V can be extended to a proper KH coloring of G if and only if this bipartite graph, the corresponding bipartite graph as we constructed, um, so this graph, just to remind you, has the neighbors, and the second part is 1 up to k, the colors, right? And the edge set we have defined here. Has a matching that saturates the neighborhood of the vertex. What do we mean by saturates? We want a matching that will match all of these vertices, right? So for every vertex, there is an available color that I can give to it. And because all of these are going to be distinct colors, at the vertex V, you will be using k distinct colors, or the degree of the vertex. Okay. Do you guys
Sir, I
believe
had
this?
a
Yeah, go
small
ahead.
clarification. So
Yeah, go
what
ahead.
if V1
Yes.
has like k neighbors?
Yeah.
So in that case, like it'll consume k colors, k different colors. So
Right. So if V1 has k neighbors, then notice that in the bipartite graph, V1 will not be adjacent
yes,
with
sir.
anybody on the right hand side,
Yes, sir.
right? And so there will not be a matching that saturates, right? So this observation takes care of that situation.
Okay. Yes, sir.
Yeah. Okay. So yeah. So if all the k neighbors, if there are exactly k neighbors and k colors, then you're not going to have a matching with the desired properties. You cannot extend the coloring. Okay. Um, Good. All right, but do you guys believe the observation? Is it convincing? Right? Do I need to explain anymore? Okay, so when any extension gives you a matching, saturating the neighborhood of V, and any such matching corresponds to an extension of the coloring to a proper k-edge coloring of the whole graph. Right? So this is just a way of formulating our problem as a bipartite matching problem, which is going to be really useful to us. Okay, great. So, um, right. So the idea behind this proof, and honestly, this is the first time I myself have read this particular proof of Vizing's theorem. I think it's really interesting, so I decided to cover this and not any of the other proofs I read before. Um, so the idea is you can think of. I'm trying to explain the maybe the discovery process to some degree behind the proof. Um, Okay, so in some sense, the idea is to prove by induction on the number of vertices. However, we will actually switch to edges. I will explain why. Okay, so we can start by induction on the number of vertices of the graph. Okay, and so inductively we can assume by induction hypothesis the graph G minus V, where V is any arbitrary vertex of the graph, has a proper delta plus 1 edge coloring, right? Good. So you take such a coloring of the graph G minus V and you construct this bipartite graph. If your bipartite graph that you construct has a matching saturating the neighborhood of V, then you are done, right? Then there is nothing else to prove. So maybe that doesn't happen. So in this case, we will modify our coloring so that the corresponding bipartite graph has such a matching. Okay, so if the corresponding bipartite graph has a matching saturating the neighborhood of V, then we are done. If not, we will modify it. Maybe somebody has joined the meeting. Okay. If not, we will modify it so that the new corresponding bipartite graph has such a matching. Okay, so this is our main idea. Since Shivam just joined, I won't go through everything, but I'll give you a quick summary of what we just did. We are taking a coloring of G minus V, and we want to understand when it can be extended to a proper K-edge coloring of the whole graph. So we are going to formulate this in terms of a bipartite graph. Your bipartite graph has two parts, the neighborhood of the vertex V and all the colors on the right hand side. And two vertices are adjacent if the color is available at that vertex as per the coloring C. Okay. So in this drawing, red, blue, and green are used at V1. However, orange and other colors are not used at V1. So I will make V1 adjacent to orange and all the other colors except red, blue, and green. Okay. And you can extend the coloring to the whole graph if and only if this bipartite graph has a matching that saturates the left hand side, the neighborhood of the vertex V. Okay, so that's an easy observation. And our idea is we are going to start by proving by induction on the number of vertices, but actually we will switch to edges for a reason I will explain shortly. Okay, so if our bipartite graph for the given coloring has a matching saturating the neighborhood of V, we are done. Otherwise, we will modify the coloring so that the new bipartite graph has a matching that saturates the left-hand side. Okay, whenever I say left-hand side, I mean the neighborhood of the vertex V. Okay, so now I want to switch to induction on number of edges and explain to you why this is a very useful trick. So I'll actually call it a trick. Well, why should I induct on the number of vertices when I can actually do something smarter? Generally, inducting on the number of edges in many cases turns out to be helpful because you see, when you remove an edge, the difference between the two graphs is much smaller. When you remove a whole vertex, you also lose a bunch of edges with that. So in that sense, induction on edges often turns out to be uh, the better way to go. And this is an example where this is really happening. So what we will do is, rather than removing the whole vertex, we will just remove a specific edge incident at that vertex. And what it will do is, it will already give us a bipartite graph where the matching is as big as possible. Let me try to explain this.
Sir,
Yeah,
just
go
to
ahead.
clarify, this delta in induction hypothesis is for G minus V, right?
No, so so delta is going to be, every time I say delta, I mean delta of G. Okay?
Okay, sir.
But we know that delta of G minus V is less than equal to delta of G, right? So we can inductively assume that the graph G minus V also has a delta plus 1 K edge coloring, right? Maybe you are not using some of the colors because delta can only be, it cannot be bigger than the delta in the original graph, right? So when I say delta, I am referring to the original graph G. Okay. Okay. So, so the trick is to use induction on the number of edges in the graph so that the corresponding bipartite graph has a matching that saturates all except perhaps one vertex. I'll explain to you why this is true in a second. Okay, so what we'll do is, we will look at our graph from the point of view of this vertex, V, and okay, I guess I'm calling them U1, U2 now, doesn't matter. U1, U2, U3, U4, U5. Okay, so this is my neighborhood of the vertex V. And let me separate out U1. This edge VU1 is E. Okay, so, well, we can assume by induction that the graph G minus E has a proper delta plus 1 edge coloring. By induction hypothesis, G minus E has a proper delta plus 1 edge coloring. Again, delta is referring to delta of G. Right? The maximum degree may either be the same or it may have reduced, but then it doesn't really matter. I can still assume that it has a delta plus 1 edge coloring, right? Maybe I'm not using some colors, that doesn't matter. So now I claim that if you assume inductively that after removing one edge, you have a proper delta plus one edge coloring, then what I want to do, okay, so I'm going to assume notation now. I'm going to drastically abuse notation. So let's call this coloring C. Okay, so C is a coloring of the whole graph except one edge, the edge being VU1. Okay, and so let me abuse notation. And when I say C minus V, what I mean is the whole coloring, except I'm going to forget the colors given to the edges incident at vertex V. So C minus V is the restriction of C to the graph G minus V. Okay, so I'm just going to forget all the colors at the vertex V. Forget these colors. Okay, good. Now I claim that this graph, so now I have a coloring C minus V of the graph G minus V, right? And now I can construct my bipartite graph as we did above. We can construct a bipartite graph for C minus V. And I claim that the bipartite graph H corresponding to C minus V has a matching that saturates all vertices in the neighborhood of V except the first vertex U1, which is the end of the edge E. Okay, why is this true? Can anybody see this? I claim that in the bipartite graph, all of the vertices can be saturated on the left-hand side, except perhaps the first vertex. So these are my colors 1 up to. Let me I won't write delta G each time, I'll just write delta plus 1. So I claim that this graph, the bipartite graph that we have, there is going to be a matching that saturates all the vertices except the first vertex on the left-hand side. Well, why? Because remember, the coloring we took is of the graph G minus E. So when I throw away the colors given to the edges incident at V, and I look at just the restriction, the specific color that was given to an edge will now be available at that vertex. Just to give you an example, if in my coloring I was using red color here, I was using blue color here, I was using green over here, and let's say I was using orange over here. When I look at the coloring of G minus V, the red color is now available at U2, blue is now available at U3, green is available at U4, and orange is available at U5. So this gives me a matching in the bipartite graph that saturates all the vertices in the neighborhood of the vertex V except the first vertex. Okay, so to make it precise, or to state it precisely in notation, the matching is here. For each vertex uj, you take the color which was given to the edge vuj as per our coloring, where j is between 2 and the degree of the vertex v. Okay, so this is a matching that saturates the entire neighborhood except the first vertex, right? Because by induction, we did not color that edge. We don't know if that last edge is colorable. We just want to make sure that somehow we can color that last edge, right? But at this point, we cannot say that. So is it clear how we constructed this bipartite graph and why the bipartite graph has a matching that saturates all the vertices except one vertex? So we now need to fix our coloring so that we can also saturate this one last vertex in the new bipartite graph. Is it clear where we are heading? Are there any questions at this point? It is a fairly involved proof, so please feel free to interrupt and ask questions. So far, we haven't done anything non-trivial. I'm just doing a setup of the proof. Okay. The reason this trick is really helpful is because we can now just modify our coloring in some local way so that we get a slightly bigger matching. Remember, we want to saturate all the vertices in the neighborhood of V. What we have right now is a matching that saturates all except perhaps one vertex, right? So the idea is to make just a slight modification to the coloring so that the new bipartite graph will have a matching that is exactly one bigger than the matching M that I have written here. Okay, and then we will know that the graph has the whole graph G is delta plus one edge colorable. Okay, good. So all right. So, in fact, so I will just say that the proof actually starts here. Okay. So if this graph H that we discussed here has a matching that saturates the whole neighborhood of V, then we are done. Does everybody agree? This is our first observation, that you can extend the matching, you can extend the coloring C minus V, which is a coloring of G minus V, to the whole graph if the corresponding bipartite graph has a matching that saturates the neighborhood of V, right? So we are going to assume, now suppose that this bipartite graph does not have a matching that saturates the whole neighborhood, right? Which means that M here is a maximum matching. You did not saturate one vertex, and we are assuming that that last vertex can actually not be saturated because of our coloring is not good enough, right? So this implies that M is a maximum matching in H, in the bipartite graph H, and that means that the graph H does not have an n augmenting path. Okay, good. So since we are talking about bipartite matchings, we are going to make our usual argument. We are going to make a usual drawing where we start from the one unmatched vertex and we look at all the vertices that are reachable by m alternating paths, right? So this is going to be very similar to the bipartite matching stuff that we did. Okay, so let Z denote the set of all vertices in H that are reachable from U1. Remember, U1 is the only unmatched vertex as per M by an M alternating path. Okay, so what does our drawing look like? Well, we have this one unmatched vertex U1. I'm going to put the left vertices on the top and the right vertices on the bottom. Okay, and we are going to have a bunch of vertices that we can reach from U1 using M alternating paths, right? So this part on the top is the neighborhood of V, and these are our colors, 1 up to delta plus 1. Okay, and well, this is a standard argument, so I'm not going to go through every small detail. Remember, our graph is going to look like this. Maybe I'll put 4 vertices just for the sake of variety. So these will be our matching edges. These are the M edges, okay? This is the unmatched vertex U1, okay? And this is Z intersection neighborhood of V minus U1, okay? And these are the Z vertices which correspond to the colors. Okay, and this is Z bar intersection the neighborhood of V, and this is Z bar intersection the colors. Okay, and since there are no augmenting paths, and these are all the reachable vertices. So remember, what does a path look like? An alternating path that starts from U1, it's going to look like this, right? You have U1 here, you take a non-matching edge, then you, maybe I should draw a non-matching edge differently. Supposing you take a non-matching edge, then you take some matching edge, then you take some non-matching edge, take another matching edge. So there are not going to be any edges from here to here, right? So all the edges in the graph will have to go like this, or they will have to go, either they'll be restricted to the left side, or they are restricted to the right side, or they go from the bottom left to the top right, but they don't go from top left to bottom right because of the definition of Z, right? Otherwise, there will be a vertex which is reachable, but you did not include it in Z. Okay, so this is our standard bipartite matching stuff. Are there any questions regarding what we have done so far, right? So there is a bunch of things going on here. We have our graph G. We took a coloring of the whole graph except one edge, and then we took a restriction of this coloring to G minus V. So we threw away all the colors that were given to edges incident at the vertex V, right? And in this restriction, C minus V of G minus V, we get the corresponding bipartite graph. This bipartite graph has a matching that saturates all vertices except the vertex U1, right? This is where we use a trick because we took a coloring of the whole graph. So we actually have one available color at every edge, at every vertex in the neighborhood of V, except the vertex U1. And we are assuming that this is a maximum matching because otherwise we would find a matching that saturates all the vertices and we would be done. There would be nothing to prove, right? So because this is a maximum matching, we can't have any M-augmenting path. And so we can make this drawing, which is based on all the vertices reachable from U1 using M alternating paths. Okay. So now we are going to analyze this bipartite graph and modify our coloring so that the new bipartite graph has a matching that saturates all the vertices in the neighborhood of V. Okay, so the plan now is to modify coloring C minus V such that the corresponding bipartite graph has a matching that saturates the entire neighborhood of the vertex V. Okay? So although we took a coloring of the whole graph minus one edge, our focus is going to be on the restriction of this coloring minus one vertex. Okay, the vertex V. Any questions or concerns at this point before we delve into further details? Okay, so the details are a bit messy. Let's see how this goes. All right. So let's start with an observation. Let's take a vertex which is in the neighborhood of V except U1. Okay. Then I claim that U, this vertex, has at least one color available in C. Why? Let's go back to our drawing. We have delta plus one colors, right? All right, supposing I take any one vertex here, let's say I take U2. The degree of this vertex is at most delta. So there's going to be at least one color which is not used by any of its neighbors, right? According to the coloring C, right? So there is at least one neighbor, at least one color available in C. Okay. And so if I were to take a vertex which is in the Z part, supposing U was here, this implies that if U is in Z, then U has at least one neighbor in Z intersection 1 up to delta plus 1 in the graph H minus M. Okay, let me explain this part. So what I want to claim to you, what I want to convince you about is if I take any vertex here on the top left part, which is different. Yeah. हाँ खिलेश रखे दो यार टेबल ऊपर. Hello. Yeah. So I want to convince you that if I take a vertex U in the top left part, then there is going to be at least one neighbor in the bottom left part, which is this is a vertex which is a neighbor of U after I remove the matching edges. Okay. Well, notice that the matching edges correspond to colors that are already used in the coloring C, right? So the reason this matching exists is because the edge UV1 was given a certain color. Let's say this is the color 1. So if the edge UV, so this edge exists, because UV received color 1 in the coloring C, right? So if this is my color 1, for example, or if you don't like 1, you can call it red or something. Okay, so the claim I'm making is that there has to be at least one neighbor, even after I remove the matching edges, for the vertex U in the bottom part. Okay, because we have delta plus 1 colors and the vertex has degree at most delta. So there is at least one color that is not used. So I can throw away the matching and I will still have at least one neighbor in the bottom. And it can't be on the bottom right side because we have already established that there are no edges going from top left to bottom right. So all such edges have to be going from top left to bottom left, right? Great. Also, what about the vertex U1? What about U1? So this is for all vertices which are not U1. Now U1 is going to have at least two neighbors. Let's see why. Let's see why this is true. U1 has at least two neighbors in Z intersection 1 up to delta plus 1. In the graph H minus M. Why is this true? I need to get some more. Okay. Right. Remember, U1 is the vertex whose one edge is not colored, the edge E, right? So at most delta minus 1 colors will be used at U1. So that will leave us with at least 2 colors that are available at U1, right? So in the case of U1, there'll be at least 2 neighbors in Z intersection 1 up to delta plus 1 after I remove the matching M. Clearly the matching M does not affect U1 because U1 is not even matched. Okay, so U1 is going to have at least 2 neighbors in the bottom left part of the graph. Great. Um, in particular, in particular, in the graph H minus M, so I'm looking at the bipartite graph, removing this matching, each vertex in Z intersection the neighborhood of V, right? So that is the top left part, has at least one neighbor in Z intersection 1 up to delta plus 1. That is the bottom left side. Okay, but note that the bottom left, its size is exactly the top left. Sorry, maybe I swapped the bottom and top. Sorry about that. Minus 1. Remember that we have exactly one more vertex on the top left part than the bottom left part, right? And we know that each vertex in the top left has at least one neighbor in the bottom left. So if you have 5 vertices on the top left, each of them has at least one neighbor in the 4 vertices on the bottom left, right? This is after removing the matching. Well, that means by pigeonhole principle, 2 of the guys on the top left, they must have a common neighbor in the bottom left. Right? So by pigeonhole, there exists X and Y in the top left and a color I in the bottom left, so that Xi and Yi are both edges of the graph H minus the matching. So what does this mean? It looks something like this. There has to be, what we are claiming is that even after removing the matching M, in fact, it is after removing the matching that we are talking about. So there is some vertex here X, there is some vertex here Y. One of them could be U1, I don't know, but they are in the top left and they are both adjacent to some common color I. Okay, and this is after removing the matching. Is the reasoning clear? Is it clear why we were able to conclude this? After removing the matching, everybody has at least one neighbor in the bottom, right? And because there is one less vertex in the bottom than in the top, 2 of the guys above have to go to a common color. They have to join to a common color. Okay, great. All right. So now, what does this mean? What does it mean for these edges to exist? It means that the color I want you to think for I as blue. We are going to put I as our blue color. The color I is available at X and also at Y, where X and Y are our 2 vertices in the top left. Okay? Good. All right. Another observation. I claim that, what about the vertex V? I claim that each color, let me explain to you why this is true. Give me a second. Each color in Z intersection 1 up to delta plus 1, so this is the bottom left, is used at V. Why is this true? All the colors in the bottom left part, they are used at the vertex V. Right, right. Um, Remember how this matching is being constructed. This matching is being constructed by looking at whenever an edge, um, yeah, if a certain edge received a color, let's say VU2 received the color red, for example, then we would have a matching edge in our bipartite graph, right? So in particular, the red color is used at the vertex V, right? So all these colors are used at V. In particular, the color I is also used at V, which is our blue color, is also used at V. Okay, great. Okay, so what do we have so far? So far we have these two vertices X and Y. Okay, these are neighbors of the vertex V, which are not using the color blue, right? The color blue is available at X and Y. And the same color blue is used at the vertex V. Okay, right? So you're expecting me to come up with a different color, right? We need two colors to do some swapping, to do some interesting stuff. So what we are going to do is we are going to take some color that is available at the vertex V. Okay, that can't be blue because blue is already used at V. So we are going to take some other color, red, which is going to be available at the vertex V. Let J, so let's say J is going to be our red color. Denote a color available at V. Okay, so where does J lie? Well, there has to be such a color, right? Because the vertex V has degree at most delta, right? We have actually not used, we have not colored one of the edges VU1. So in fact, there'll be at least two colors that are available at the vertex V. So let J denote a color available at V. So then where does J lie in our bipartite graph? I claim that J has to be in Z bar intersection 1 up to delta plus 1. In fact, it has to be one of these unmatched vertices. So J will be something like here. Remember the bottom part is the colors, right? I is a color blue, which is on the left side. and J is going to be one of our colors on the bottom right side. It will be an unmatched vertex because it corresponds to a color that is available at the vertex V. So it can't be part of the matching, right? Because the matching edges, they correspond to colors that are not available at the vertex V, right? Um, and it also follows from the observation that I just made earlier. Okay, good. Um, Great. So I want to make another claim about this color J. Um, okay, I want to claim that J is used, so J being our red color, is used at each vertex in the top left part. Why is this true? Can anybody tell me why this is true? Why is J used at each vertex in the top left part? I will give you a hint. Try to remember how we constructed this bipartite graph. If the color J was available for some vertex on the top left side, let's say Y, then Yj would be an edge of the graph, of the bipartite graph. But we know that there are no edges going from the top left to the bottom right. That means that the any color you see on the bottom right part, including the color J, all of these colors have to be used in all the vertices in the top left side, because otherwise the color would be available and you would have that edge. We know that such edges are not there in our bipartite graph, right? So the color J has to be used at every single vertex in the top left part. Okay, that includes the vertex q1, but it also includes all the other neighbors of the vertex v, which are in z. Okay, so proof: if not, um, there exists an edge in the bipartite graph H from top left to bottom right. Contradiction. We know that such edges don't exist. Okay, so the color red is used at all the vertices in the top left part. In particular, red is used at x and y. This is what we are going to care about. In particular, J, which is our red color, is used at x and at y. Okay, good. All right. So now I want to make a nice drawing. Let's see. Are there any questions at this point? There is a bunch of details, I agree, but hopefully we are going through each step gradually. Okay, so I want to make a better drawing of what all is going on in this proof. Let's say this is my vertex V. Maybe this is too big. Okay, so I have a vertex X here. I have a vertex Y here. There is a vertex U1. X or Y could be U1, but let's not worry about that case. The proof works out. Okay. So X and Y, the red color is being used at both of them. Okay, and blue is being used at the vertex V, but blue is available at X and also at Y. So let me just put a note here. Blue is available at X and at Y. Okay. Um, all right. Blue is being used at the vertex V, and red is available at V. Blue is used at this vertex V. So there is some blue edge here. And red is available at V. Okay, good. Okay, so we don't know exactly what the whole graph looks like, but we have some information that there are red edges at X and Y, but there are no blue edges at X and Y. There is a blue edge at V, but there is no red edge at V. Okay. Great. So now we are going to do the usual business. We are going to look at the red-blue subgraph of this graph. Consider the graph Gij formed by red and blue edges. Okay, so we are looking at two matchings and we are looking at the union of those two matchings, right? All right, so we know that these are vertex disjoint paths and cycles. So Gij, we know it is a collection of vertex disjoint red blue paths and cycles, right? What about the vertices Vx and Y? Each of these vertices is a vertex of degree 1 because each of them either has the red color and does not have the blue color, or vice versa, right? Also, each of V, X and Y is a vertex of degree 1 in the graph Gij. Okay, great. All right. So what that means is that each of them is an end of some path, right? They can't be in a cycle. So each of them is an end of some path component. All right. So what's our plan going to be? We are going to take one of these paths and we are going to swap the red and blue colors there. And then we are going to think about that and relate it to our bipartite graph. Of course, the new coloring will give us a new bipartite graph, but because the coloring will be only slightly different from the original one, we will be able to analyze the new bipartite graph based on the old bipartite graph. And we will gather just enough information to show that the new bipartite graph has a matching that saturates that one last vertex U1. Okay, we have already saturated all vertices except U1. We just need to saturate that one last vertex. When we get such a bipartite graph, coloring for which this is true, then we know that that coloring can be extended to a coloring of the whole graph G. Right? So this is going to be our plan. We are going to take one of these path components and switch the colors. I think we'll go on till about 6 p.m. today. Okay. Good. All right. So let P denote a path in Gij whose one end is X or Y and other end is not the vertex V. Let's see why this is true. Why does such a path exist? Well, maybe the path which contains X, maybe it will end at the vertex V, but then you would take the path containing Y, right? And then that would not end at V. Okay. So in all cases, you can go through the analysis yourself easily. You will always be able to find a path whose one end is X or Y, and the other end is not the vertex V. Okay, that's not difficult to see. Okay, basically we don't want to make changes at the vertex V. We want to keep the vertex V as it is. Right? We want to make the changes in the graph G minus V. Okay. All right, so we have this path P, and we may adjust notation by relabeling X and Y. So that X is an end of P, and we let W, so W could be Y, for example, we let W denote the other end of this path. In particular, W is not equal to V. Okay, so what we are doing is we are taking some path. I'll just make a schematic figure here. It's a path like this, right? And maybe this is a vertex W. Although W could be somewhere else in the graph, I'm just drawing an example. Okay, so this is our path P. All right. So now we are coming towards the end of the proof, but it's still some way to go. Okay, so bear with me. I think another 15 minutes should be enough to finish the proof. Are there any questions at this point? Is it clear how we have reached until this point?
To a decent extent, sir.
Yeah, go ahead, Surya.
Yes, sir. Like, to a
Sorry?
to a moderate extent, it's clear.
To a
I
moderate
think I need to go
extent.
through it again
Good.
to get it perfect.
Yeah, sure. No, I totally get it. This is an intricate proof. I had to read it 4 or 5 times before I could prepare the lecture. So yeah, so definitely there are lots of details that you will want to go through again. But yeah, if you are following to a decent extent, then that's good enough. Okay, good. So, all right. So let's start. Let's finish what the remaining details are, and then we will go back to some arguments which may not have been very clear. So C prime is going to be a new coloring of the graph G minus E obtained from C, okay, by swapping the colors I and J. By swapping I, which is, remember, blue, and J, which is red, on the path P. Okay, so we are going to just swap colors on this path, and notice that this path does not contain the vertex V, right? We chose the path in such a way that the other end is not the vertex V. So what that means is that none of the edges incident at V, their colors have not been affected. Okay. Um, since V is not a vertex of the path P, C and C prime coincide on the coloring around the vertex V, where the edge E is not colored because, well, E was not colored to begin with. Okay, so these colors coincide exactly on the partial of V minus the edge E. Um, using notation again, abusing notation again, let C prime minus V denote the restriction of C prime to G minus V. Okay, so again C prime minus V is going to be the same coloring as C prime. We are just going to ignore the edges at vertex V. And let H prime denote the corresponding bipartite graph. Okay, so is it clear? We got a new coloring of G minus E. We are looking at its restriction to G minus V. So we are ignoring the vertex V. And we get a corresponding bipartite graph, H prime. Right? All right. Notice that because we did not make any changes around the vertex V, the matching M that existed in the original graph H, it also exists in the new graph H prime. These observations imply that M is a matching of H prime as well. Okay. So the question I want to ask is, where exactly do H and H prime differ? We are not making that many changes. We have just changed the colors on one specific path, right? And one of the vertices where changes occur is the vertex X, which belongs to the neighborhood of V. So there will be a change there. And then notice that on the path, the availability of colors does not change. If you just swap red and blue, the availability of the colors is not going to change. The availability of colors only changes at the ends of the path, because a red color would be replaced by a blue, and so the availability would be changing. But at any intermediate point in the path, the colors used are exactly the same. Right? So the changes will be either at x, partial of x, and they will be at partial of w if w is part of the graph H. But if w is not a neighborhood of v, is not in the neighborhood of v, then there will be no changes for that. So they differ only in partial of x, and x being our small vertex, and possibly in partial of W if W is a neighborhood in the neighborhood of the vertex V, right? But W may not be in the neighborhood, so then it will not have any changes there. Okay, so is this part clear that the two graphs H and H prime, they do not differ by a lot? Okay, great. All right, so now we need to finish the proof. So now the plan is to show that H prime has an M augmenting path and thus a matching that saturates the entire neighborhood of the vertex V. And then by our first observation of the lecture, C prime minus V can be extended to a proper delta H, yeah, to a proper delta plus 1 edge coloring of the whole graph G. Okay, so we will just, this is where we are using the fact that we already have a big matching. It just misses out one vertex. So now if we just show an M augmenting path, then we will have a matching that saturates all the vertices in the neighborhood of V. And once we have that, we know by our very first observation in the lecture that this matching, this coloring C prime minus the vertex V can be extended to a proper delta plus 1 edge coloring of the whole graph G. Okay, so this is our last part that remains to be done. Okay, so let's get started. So I want to show you the existence of an M augmenting path in the graph H prime. So we will start with H because H is a graph we understand. So let's say in H, we know that there is an M alternating path. From the vertex U1 to X. Let me just remind you why this is true. Let's go back to this drawing. Remember, Z is a set of all vertices that are reachable from U1 by M alternating paths. In particular, X is reachable from U1. So you can find an M alternating path from U1 to X in the graph H. Okay, so let's take our path Q. I want to show you that this path Q can be converted into an augmenting path in the graph H prime. So there are two cases. Either W is not a vertex of this path Q. Okay, so W is the other end of our path P where we made the swapping of the colors, right? So remember that P is a WX path. Okay, so what does this path look like Q? U1, then you have a, maybe I'll draw the matching edges as curvy edges. So this is a matching edge. And let's say now you reach the vertex X, right? Okay. All right. So this is our path Q. Okay. Note that since W is not a vertex of Q and all the edges of M are also edges in H prime. Remember the matching M continues to exist in H prime, because we did not make any changes around the vertex V. So that matching is still a matching in H prime. So this means that Q is an M alternating path in H prime as well. So this path that exists in H also exists in H prime. However, an interesting thing has happened. Now the color J, red, has been made available at X. Remember, X was using the color red, but now we have swapped blue and red. So red is actually now available at X. And where was red in our original drawing? Red was one of these unmatched vertices. So now this red color is available at X and it is an unmatched vertex. So that will give you an M augmenting path. Furthermore, J, which is the red color, is available at X. This implies that Xj is an edge of H prime. And recall that J is actually M exposed. So if you just take this last edge, if you add one more edge to this, which is the edge xj, this edge belongs to the graph H prime. And now what you have is an augmenting path from U up to J. And so you get a bigger matching, and that finishes the proof in this case. So Q plus xj is an M augmenting path in H prime. Okay, so this is the first case. This is the easier case because the vertex W did not interfere with our life. Case 2 is when W is on our path. Okay, so W is one of the ends of the path P, right? And basically before we run into the path, before we run into the vertex X, we will first run into the vertex W, right? Because the path goes from U1 to X. So if W is on the path, it has to be somewhere between U1 and X. Yep, so the drawing looks like this now. We have a matching edge, the vertex X, this is U1, and W is someone here. Okay, great. So we are going to do something very similar actually. Rather than going all the way to X, we are going to stop our path at W, and we are going to add the edge Wj to get the augmenting path. So I'll just put down the details. So let Q prime be U1 Q W. So Q prime is basically this part. And this whole path I've drawn here is Q. Right? Notice that Q prime exists in the graph H prime for the same reasons as in the previous case. Note that, as in previous case, Q prime is an M alternating path in H prime. Right. Good. Also, where is the vertex W? W is a vertex in Z intersection the neighborhood of V, right? Because, well, W is reachable by an M alternating path, so it has to be in the top left part of our graph, right? So that means that as per the coloring C, the path P ended at W using color J. So in the original coloring, you would have to end the path P with the color J, because it is only the I think at some point we argued that it is the red color that is used at every vertex in the top left part, right? So it would have to end with a red colored edge. And as per the new coloring, it would be ending with a blue colored edge, right? And as per C prime, P ends at W using color I, which is blue, right? So as per C prime, red is now available at the vertex W. As per C prime, J being red is available at W. And what that means is that Wj is an edge. So there is an edge from W to the vertex J, which is our red color. And this will be our augmenting path. You start from U1, you go up to W, you follow the path Q up to W, and then you add the edge Wj. So it's very similar to case one. You just need a little bit of more argument to establish that this is an edge in the graph, Wj is an edge of H prime. This implies that Wj is an edge of H prime, and also recall that J is M exposed. So now, as before, Q prime plus Wj is an M augmenting path in H prime. And actually that finishes the proof, because in both cases we found an M augmenting path, right? That means that our original matching is not as big as possible. You can make it bigger to saturate every single vertex in the neighborhood of V. And that means by our plan that we discussed, that C prime minus V, which is our new coloring minus the vertex V, it can be extended to a proper delta plus one edge coloring of the whole graph. Right. So that's it. We basically reduced proving Vizing's theorem to bipartite matchings. Right. Okay. So are there any questions? I guess, Surya, you're the only one here. So is there any part you would like me to go through again?
I guess I need to go through the proof once again, Mr. Fan.
Sure.
Then I'll have to
Yeah.
ask if there are any questions.
Yeah, sure. There are lots of details. It's mostly the same proof from the text. I think I made some notational changes which may end up being a bit confusing, but for the most part, I have stuck to the proof in the text. Okay, so go through it again, and yeah, I think this is one of the most intricate proofs we have done in the course so far. There is a lot of details. All right. Good. So I guess if there is no specific question at this point in time, we'll just meet you on next week.
Yes, sir. Okay. Thank you, sir.
Yeah. Okay. Okay. Thanks. Yeah. Bye.
Bye, sir.